for this problem, what we are going to do is come up with a circuit that will produce the finite state machine described by this state assigned table. So that's what we're going to do here. This little thing is not, I was going to type something, but it's not part of the problem, so you can ignore that part. So one thing that might be, it's not really useful in terms of getting the circuit, but it is useful for knowing what's going on, is to kind of go a little bit backwards. And for me, it's easier to think of these states not as binary numbers, but to give them names and then look and see what happens. So before I do this, what I'm going to do is I'm going to first draw the state diagram, which is not part of the problem, and it doesn't really help with the problem. I'm just kind of adding it as something additional to do so you can see where it comes from. So if I rewrite this table, and when I rewrite it, I'm not putting the y2 and y1 because I'm just going to be referring to these as names. And I'm going to say that 0, 0 is state A, 0, 1 is state B, 1, 0 is state C, and 1, 1 is state D. So these are my states. And then my next state, 1, 0 is C, 1, 1 is D, 0, 1 is B, 0, 0 is A, 1, 1 is D, and 0, 0 is A, 1, 0 is C, and 0, 1 is B. And my output is given as that. So notice that the output does not depend on the input. I only have one column, that my output depends only on what state we're in. Okay, so on this one, you'll see that the output does not depend on the input. I only have one column, and the output is from the present state. So that means this is a Moore machine. So Moore output does not directly depend on input. And so when I draw my state diagram, I'll have my states A, B, C, and D. And because my output depends just on the state that I'm in, I can put the output right there on my state diagram. Z equals 0. On all of them except for state D, where Z equals 1. And then I only have one input, which is W, and so W will tell me what state I go to. So for each state, I need to see what happens for every possibility of the input. There's only one input. It can only be 0 or 1. And so if I'm in state A and W is 0, I go to C. And you can indicate that. I like to write it as W equals 0, but you can also just indicate it as W bar. And if W equals 1, you would go to D, and so that would be W. You could also write it as W equals 1. From state B, if W equals 0, I go back to B. So that's W bar. If W equals 1, I go to A, so that's W. And if I'm in state C, if W equals 0, I go to D. If W equals 1, I go to A. And if I'm in state D and W equals 0, I go to C. And if W equals 1, I go to B. So all of that was just to have practice with that, so it doesn't help us draw the circuit. We're going to do that on the next slide. Okay, so we need to do 2 Carnot maps, one for Y2, capital Y2, and one for capital Y1. And our Y2, I'll start with Y2. Y2 is this column right here and this column right here. And it depends on lowercase y2 and y1 and also on W. So my Carnot map will have lowercase y2, y1, and W. W can be 0 or 1. And y2, y1 can be 0, 0, 0, 1, 1, 1, 1, 0. Now be careful, and someone noticed this in a session not too long ago. They had forgotten from 2741 that the Carnot map is not in numeric order. It goes 0, 1, 1, 1, 1, 0, whereas usually when you list them in numeric order, it'd be 0, 0, 0, 1, 1, 0, 1, 1. So this is not in the same order as my state table, so just be careful about that. And I'm going to start with W equals 0. So W equals 0 is this first column right here. And so for 0, 0, I get 1. For 0, 1, I get 0. For 1, 0, I get 1. And for 1, 1, I get 1. And I'm doing just Y2 right now. So now I'll go to Y2 in the second column, and this is when W equals 1. And I get a 1 for 0, 0, and 0s everywhere else. So the best cover for this is those 2 circles. And the vertical one here is, so this is capital Y2 equals not Y2 and not Y1. Lowercase y1. Now we'll do Carnot map for y1. Do you want to try to do it on your own and then check it, or do you want me just to do it? So for the video, I'm going to pause it right now and let you who are watching this try it on your own. So if you're watching this on the video, stop the video, try it on your own, and then you can start the video back up and check and see if you're right. So be careful when you're filling out your Carnot map, because the Carnot map, the order on top is 0, 0, 0, 1, 1, 1, 1, 0. And when you look at the order in this state table, we have 0, 0, 0, 1, 1, 0, 1, 1. So when you're looking at the numbers in this column, 0, 1, 1, 0, these bottom 2 are not in the same order as they are in the Carnot map. So if you wanted to write them in the same order, it'd be 0, 1, 1, 1, 1, 0. And then so we're swapping these bottom 2 rows with each other. So that's why it's like that. Okay, so what you should get if you do the Carnot map is you have, it's alternating 0, 1, 0, 1 on top and then 1, 0, 1, 0 on bottom. This is a Carnot map that gets something that just is as unsimplified as you can get. There's no way to get any groups on it. But we do have a trick up our sleeve that will make our circuit not have to have quite so many gates. And that trick is that we have an exclusive OR gate, and an exclusive OR can be used to, as if you're building a circuit, you can use one gate that if you're just using ands and ors and nots, it would take more. So okay, so what an exclusive OR does is if I have x bar y, exclusive OR x y bar, I'm sorry, if I have x bar y or x y bar, that's equivalent to the exclusive OR of x and y. So the exclusive OR of x and y is the same as x bar y or x y bar. And you can see that if you look at the exclusive OR table. So if I had x, y, 0, 0, 0, 1, 1, 0, 1, 1, and then I want to look at the exclusive OR. So the exclusive OR means that one of them is 1, but not both of them. So I have a 1 here and a 1 here, a 0 here and a 0 here. So this is the same as saying that I have either x is 0 and y is 1, or x is 1 and y is 0. So that's an exclusive OR. So if I take a look at this function right here, and I factor a w bar out of the first two terms, and then I have y2 bar, y1, or y2, y1 bar, and I factor a w out of the second two terms, y2 bar, y1 bar, or y2, y1. This w bar, that right there is what we got. That's our definition for the exclusive OR. So that's y2 exclusive OR y1. Or, now if you look at this second one, I'm going to take this truth table that I wrote right here, and I'm going to take the conjugate, or the complement of this column right here. So I'm going to take the complement of x exclusive OR y, and I get 1, 0, 0, 1. And so if I put these two together, that would be x bar, y bar is, I'm sorry, that's the first two would be x, y. So I have either x and y, or not x, not y. And that's what I have right here. So this second one is the not of the exclusive OR of y2 and y1. Now, if you look at what I've got here, I've got w bar and w, and I have y2 exclusive OR y1 and the not of that. So I actually have the exclusive OR of these two items right here. I have w exclusive OR y2 exclusive OR y1, and with exclusive OR it doesn't matter what order you do them in. So this is w exclusive OR y2 exclusive OR y1. So that is a way that we can build a circuit that's slightly smaller than if we used all these gates. Now also, if you just look at the function that we had, which was y2 bar, y1, w bar, plus y2, y1 bar, w bar, plus y2 bar, y1 bar, w, plus y2, y1, w. This one is the exclusive OR if you have two things, we say the exclusive OR is equal to 1 when one of them is 1 but not both of them. If you have multiple things that you're taking the exclusive OR, so multiple items with exclusive OR, the exclusive OR equals 1 if you have an odd number of 1s and it equals 0 if you have an even number of 1s. So, for example, 1 exclusive OR 1 is 0 because I have an even number of 1s. 1 exclusive OR 1 exclusive OR 1 is 1 because I have an odd number of 1s. I can add as many zeros to this as I want and it doesn't affect anything. It's just the number of 1s that tells you whether or not your exclusive OR is equal to 1 or not. And so if I think about having 3 variables, y2, y1, and w, and I come up with all of the ways that I can have an odd number of 1s, well, I could have y1, 1, and y2 and w 0, or I could have y2, 1, and y1 and w 0, or I could have w1 and y2 and y1 0, or I could have all 3 of them equal to 1, and that's also an odd number of 1s. So what we wrote here is every possible way to have an odd number of 1s, which is the exclusive OR of 3 variables. So that was just a little bit extra about exclusive OR. Okay, so now let's draw our circuit. We have the functions that we just got were w exclusive OR y1 exclusive OR y2, and that was for y1. And for y2, we got w bar y. Did we do write it out for that one? Did I not finish writing it? I don't think I wrote the first. I think I wrote y2 bar y1 bar, but then I don't think I wrote the second term in it. So this second term I didn't. The second term is y2, where y2 is 1, and w bar. Yeah. So y2 is when I go to draw the circuit coming up. I'm going to draw this circuit as if my y1 and y2 are separate variables the way they look like they are here in the table. But y2 and the capital, the lowercase letters, are really the same as the uppercase level letters after the clock cycle. And so once you have the output from the flip-flop, the lowercase letter becomes the uppercase letter. So when I have lowercase y1 as an input in here, the output is a capital Y1. So really, this separate lowercase y1 is not a separate variable. It is really the output coming back in to be the input. So when I start drawing the circuit, I draw these lowercase y1s as if they're separate variables, but they're really not. And then when I get done drawing the circuit, I will go in and I'll erase these and I will connect them to the output. Is y1 bar, y2 bar, or w bar y2. So then, and we want to use D flip-flops to make this. So we're going to have 2 D flip-flops. The reason we have 2 D flip-flops is because we have 2 variables. We have a capital Y1 and we have a capital Y2. And that's what our outputs are here. So there's, this is, I'll make this one Y1 and this one y2. Plot. And then for y1, my input is the exclusive OR of my three variables. So w, y1, y2. And I can do this with a 3-input exclusive OR gate. So I'll do that. And that'll be my input. And this will be D1. This is D, this is Q. There's D. This one is going to be D2. And D2 is Y1 bar and Y2 bar. These are supposed to be lowercase y's. And W bar Y2. And then I want the OR of those. Okay, so that gets me my output, so that gets me my next state. Sorry, it doesn't give me my output, it gets me my next state, but we still have to get the output. So let's go back and look at the output. And remember, the output depends only on the present state. So it's going to be a real easy Carnot map because it only has two variables. It just has y2 and y1. And when they're both 0, well, the only time our output is 1 is when they're both 1. And so z equals y1, y2. And so on our circuit, we would take okay, but I have an issue here because this is not a sequential circuit because I have a separate y1 here and y2, and the capital Y1 and the capital Y2 are supposed to be the next state. And so once Y1 and Y2, you have your new values of Y1 and Y2, they become the present state. So really, this Y1, this capital Y1 and capital Y2, those are, once you output them, that is lowercase y1, and this is lowercase y2. So we really don't have these separate inputs here at all. So you could draw them like that to start off with, but they certainly are not part of your final answer. Now, since our output depends only on our present state, and our output was, what did we say it was? It was y1, y2. Then our output is just the AND of these, and that would be Z. And that's our circuit.